Okay, so this is lesson 14, and we're going to start off by just doing one last application of dot product and cross product. And this here is the idea of torque, and we kind of referenced it already because we talked about this idea of turning a wrench, all right, and the fact that you've got two vectors that are involved in this idea of turning a wrench, because you've got the distance away from the pivot that you're applying the force, and then, of course, there's the force itself. Okay. So this idea of torque is that sort of turning force that creates this rotational motion about an axis, about this pivot point. Okay. And the way we define that force is we define that force as being perpendicular to both of the two forces. Okay. And it follows, as we talked about, this idea of the right-hand rule. Okay. That if I start in the direction of the radius. Okay, so here, let me draw a diagram here just to show what we're doing. So let's say we use the idea of the wrench. Okay, so here's the screw that I'm turning. And so what we have is we have what's called the radius vector. Okay, we'll call that R. Okay, and then what we have is we have the force that's being applied. Okay, so say I apply a force like this onto the wrench, all right, and the idea of torque is that it's the cross product of these two vectors. Okay, now let's see what that would look like if we're talking about cross product. So say I take this force vector and I place it tail to tail with this radius vector. So there's my force vector that I'm applying. And remember what the right-hand rule said. Okay, the right-hand rule said that if I go in the direction of the first vector, so that's my radius vector, and then I go in the direction of the force vector, okay, you got to imagine where's my thumb sticking out, and we see that the force that's produced is going, or sorry, the vector that's produced, which is your torque vector, is going into the page. And that follows our righty-tighty rule, that if I push towards the right, or I apply a force towards the right, I'm going to get the motion of the screw going into the page. Whereas if I were to apply the force in the other direction, so now this becomes my force vector. So let's do the same thing. Fingers in the direction of the radius, curl towards the force, and lo and behold, where's my resultant vector? My torque vector is going outside of the page. So there's the lefty-loosey rule. Okay. So what we have here is we have the torque, which is represented by the Greek letter tau. So the torque vector is given by R cross F. Okay. Now, mathematically, we know that order is going to make a difference. So it's very important that I write R cross F when you think of work, which is a dot product. It doesn't really matter what order you put it in, but for torque, it does. And we just saw that if I do the vector, so let's now, if I try to do this vector here, okay, my original radius vector and the force in my righty-tighty, if I try to do force cross R, there's my force vector. If I curl towards the R vector, my resultant vector is going in the wrong direction. It's going in the opposite direction, which makes sense because we saw that cross product was not commutative, but it was anti-commutative. All right. So the units here. So if you imagine, think back to our geometric definition of the cross product. Okay, magnitude of R times magnitude of the force times sine of the angle between them. You see that you've got the magnitude of the radius vector is going to be in meters, and the magnitude of the force vector is going to be in newtons. So what we do is we say Newton meters. This is these are the units of torque. Now, do you recognize where else we had newtons multiplied by meters? Where else would we have seen that? Okay, you had work, okay, which becomes joules. Okay, but the thing is that torque is not really related to energy in the way that work is related to energy. So despite the fact that the textbook calls this joules, my understanding is that the convention is that for torque, we don't use joules, is we leave it as Newton meters, okay? So I'm a bit surprised the textbook goes that way. Maybe it is acceptable, but you know, from what I remember, torque, we leave it as Newton meters, okay? So in terms of how you solve problems involving torque, similar to work, is going to be dependent on the type of information that you're given. So if the information that you're given is geometric in nature, then you're more than likely going to work with the geometric definition of torque. Whereas if you're given information in terms of algebraic vectors, then you'll work with the algebraic definition of cross product to calculate torque. Okay, so just to recap, okay, your torque is this quantity given by r cross f, so where r represents the vector from your pivot point, okay, from your axis to where you're applying the force, and then the force is, well, just the force that you're applying, okay? And keep in mind that if you're trying to picture how these things behave with respect to each other, especially with respect to the angle, don't forget that these vectors have to be placed tail to tail when you're talking about the angle, all right? And very big thing to keep in mind is the order in which you carry out this cross product is going to be important, because if you carry it out in the wrong direction, you might get the correct magnitude, but you're not going to get the correct direction. Okay, so if you're working with algebraic vectors, the direction is incorporated in the final vector that you get algebraically. Whereas if you're working geometrically, don't forget that you have to use your right-hand rule to solve the problem. Okay, so in the direction of the r, curl towards the f, and in this case here, where's the direction of the vector? Going into the page. All right, any questions on how we defined torque? Okay, and by the way, this is not the only physics quantity that's defined using using cross product. There's also another common one is with electric and magnetic fields. Okay, cross product comes up in that scenario. Okay, any questions here we want to ask? Okay, so what I'm going to ask you to do is I'm going to ask you to take a couple of minutes and work on this one here. Okay, so I want you to keep in mind how the information is given. Okay, that might help you decide how to solve the problem. And you know what? If you need a diagram to help you out, not a bad idea to draw yourself a diagram, even if it's not, you know, sort of a fully formed, you know, wrench as I drew there. Okay, so we're back. Let's take a look at this question here. So it says a 50 Newton force is applied to the end of a 20 centimeter wrench and makes an angle of 30 degrees with the handle. They want us to find the magnitude of the torque, and they want it to determine how we could achieve the maximum torque. All right. Now, first of all, do you notice a little thing that we're going to have to keep track of here? We've got the geometric definition of the geometric definition I work with, because here nothing's given algebraically. Okay, we just have everything given geometrically. So I'm going to draw myself a diagram here, and I'm not going to be as, you know, not going to be as precise as I was before. So let's say here's my pivot point. Okay, now say this is the length of my wrench, okay, because it's being applied at the end of the wrench, okay. Now, here I notice that I'm tightening, okay. Now, it shouldn't matter because I'm only looking for the magnitude, but can you see that I'm going to have to apply my force in that direction and not in that direction? Because I know that if I want to tighten it, I'm going to be applying it towards the right. Okay. Now there's one piece of information that's not very clear. It says an angle of 30 degrees, but can you see how, it says an angle of 30 degrees with the handle. Okay. So they're not saying, 30 degrees with respect to, the other vector here. We're not talking about the radius vector. They're just talking about with respect to the handle. So it's not necessarily clear whether I'm applying the force like this at 30 degrees to the handle, or if I'm applying the force like this at 30 degrees to the handle. Okay. Now, can you see that that will make a difference? When is this going to make a difference here? Because what am I eventually going to have to do with this force vector? When I'm calculating my cross product at a certain point, what am I going to have to do with this force vector that was described with respect to the handle?
You need to use sine.
Yeah, I'm going to use sine, but what angle am I going to be actually using in my calculation? What angle does this represent? There you go. We're going to move it tail to tail. Okay, so depending on how I interpret this question, if I move this vector, there you go, I'll have it at 30 degrees. But if I look at this vector here, it's actually going to be, well, what are we going to have here? What angle would this be here? If that's 30, what's that angle going to be? It's going to be 90. Okay, there you go, 120. So let's see what happens. Out of curiosity, let's see what happens in these two scenarios. Okay, so in this case here, let's take a look. We've got our torque vector. We're looking for its magnitude. So magnitude of r times magnitude of f times sine of the angle between them. So here, if I take option number 1, okay, well, the radius vector, it's being applied at the very end of this wrench. So we just have 0.2. Here, I've got 50 newtons of force being applied. And let's see what happens when I use option number 1 with sine of 30. Okay, so let's get our trusty calculator here. And what do we have? We have 0.2 times 50 times sine 30. And there we go. We have 5 Newton meters. Okay, now let's take option number 2 here. And let's say we had taken the other scenario where we're pushing on the wrench in that direction. Okay, so sine of 120. So again, 0.2. Actually, wait, this is not 120 here. There you go, because sorry, this should be 30 here, so it should actually be 150. Okay, sorry folks, I'm a little off this morning, clearly. Okay, so here 50 times sine 150. And let's see what we get here. Now, before I even type this in, can somebody tell me what I'm going to get? Think about sine and think about these two angles. What answer should I get? I should get the exact same answer. So let's check that we do. 0.2 times 50 times sine of 50. Sorry, sine of 150, and you still get 5 Newton meters. Now, what mathematical principle explains that we should get the exact same answer here? What's the mathematical principle? Okay, yeah, let's be a little more precise. Certainly trig. So what's that mathematical principle that we determined back in advanced functions that explains why this should be happening? Well, remember, if you have some angle in the first quadrant, and then you take the other angle, there you go. Okay, that if you take this same related acute angle and you take, well, we saw it as pi minus theta. Here, obviously, it'll be 180 minus theta. And we know that because sine is positive in both these quadrants, we have that sine of 180 minus theta is equal to sine of theta. So it makes perfect sense that these should give you the same answer. So whether I push on this, as long as it's 30 degrees from the wrench, whether I push from this side or I push from that side, I produce the same torque. So now the question is how would I be pushing, okay, so that I produce the maximum torque? How should I be applying my force in this scenario here, given that the wrench is 20 centimeters long, given that I'm applying 50 newtons of force? How would I achieve the maximum amount of torque? So how would I be pushing on this wrench? There you go. Now, intuitively, and I'm sure if you think about it intuitively, it makes sense to apply the force directly onto the wrench at a 90-degree angle, okay? You would imagine that that's the most efficient way of doing so. And of course, what you want is you always want the math to be in line with your intuition. And when you think of this formula, if R and F are fixed, why does it make sense that applying it at a 90-degree angle would give you the maximum torque? So what's the mathematical reasoning that justifies, that's in line with our physics reasoning? There you go. If these are fixed, where does this part achieve its maximum? It achieves its maximum at 90 degrees. So sine of 90 degrees, which is equal to 1, is the maximum value between 0 and 180 degrees. Okay? So just to kind of finish off this idea of torque and this idea of creating a turning motion, okay? So let's think about how we could maximize the torque. So we now see that applying the force at a 90-degree angle as opposed to any other angle is going to maximize the torque, okay? Clearly, applying more force will maximize the torque. What is the other thing to keep in mind, okay? What else do you want to try to maximize if you're trying to turn this lever? What's the other thing you would try to do to maximize the amount of torque produced? There's one thing left. There you go. Okay. Well, I'm not sure if I understand that, because are you talking about the direction in terms of the angle, or what do you mean by direction? There you go, is how far you are from the pivot point, okay? And the best example is to go to one of your doors in the house. Presumably you've got a door somewhere in the house, and, try to apply a force to the door to open it up, just open it and just sort of push it here with a light force, and you'll probably see that the door starts to slowly open. Try applying that same amount of force right near the pivot point, and you'll probably see that the door is not going to move, okay? So the way in which so that's why when you're, unscrewing something, you don't want to try to unscrew it this way. You want to try to apply the force as far away as possible. So intuitively that makes sense, but the math also confirms that if I try, the idea is to try to maximize each of these three portions: the angle at which you're applying it, the amount of force you're applying, and how far you are from the pivot point. All right? So apologies for the little numerical mistakes there, but let's move on, because now we're actually going to move on to a completely different topic, okay? Now, I say it's completely different in terms of our focus, but we're going to see that we're going to use a lot of the tools that we've developed in this whole portion. So not so much in terms of the physics application, so not so much in terms of things like velocity and force and torque and work, but all those tools working with vectors, in particular algebraic vectors. So the first question I have, okay, is we know how to define a line in 2 dimensions. Okay, so here's one version of it. So we have the standard equation of the line. All right, so say now I want to start talking about lines in 3D, because that's where I said we were going. We're going to start doing some analytic geometry in 3D. So we're almost going back to grade 9, okay, but trying to do everything in 3D. So if you had to just, based on what we've seen, that question in the homework about the sphere, and you realize that the equation of the sphere looked a lot like the equation of the circle, if you had to make a guess as to what the equation of a line would look like in 3D, what would be a reasonable guess based on this equation of a line in 2D? So who'd like to suggest what the sort of reasonable, if you're just going by what we've seen so far in terms of how things have progressed from 2D to 3D, what would the equation of a line, what might you think it would look like? There you go. That's a pretty reasonable, okay, that it would look like ax plus by plus add in a z portion equals d. Okay, so the question is, does this represent a line? Okay, so let's come up with an example here. So let's say I come up with an example of, I don't know, x plus y plus 2z equals 6. Okay, so I just picked something easy where the numbers are easy, and let's try to figure out whether this does indeed represent a line. Okay, but you have to remember that in terms of working in 3D, so we can find points in 3D, and the only other thing we really know how to do here, because we don't really have a concept of slope or anything like that, so we do have the concept of vectors. So can anybody suggest what we could do? Okay, now notice here, I'm giving you the suggestion that we work with 3 points. So if I have 3 points and they lie on a line, what could I do to show that the 3 points indeed do lie along the same line? How could I use the concept of vectors here to help me check that they do lie along the same line? Because really, that's the only tools I have. Any ideas as to what I could do? Okay, so I could find, so you mean like find the unit vector in this direction, unit vector in that direction? Okay, and then that makes sense, because then, yeah, you would be able to see if they're the same vector. Oh, okay, that's a good one. Okay. So another suggestion is compare vectors PQ and QR. Okay, so let's say I take these 2 vectors and those two vectors. Well, what would have to be similar with respect to these 2 vectors if those points all lie on a straight line? What would they have to have in common if those 3 points lie on the same line? Oh.
Would they have to have 2 sets of variables that were the same?
So let's say what I'm going to do is I'm going to actually work with 3 specific points. I'm going to work with 3 specific points. And what I'm asking is, if those points lie along the same line, what would have to be special about these 2 vectors that I just created? There you go. They should be parallel, because that's what we call lines. They're collinear. They're parallel. So in the end, it's very similar to the idea of finding the unit vectors. I think it might be a little faster, okay, is to compare the vectors PQ and the vector QR, and we should be able to tell fairly quickly whether those 2 vectors are parallel to each other, okay? And we know that would have to happen if they all lied on the same line, okay? So here, if I say, let's start picking, so let's say P, let's just start creating, and I think this is fairly easy. The numbers are nice, so let's just do this by just looking at it. So let's say I pick X equals 1, Y equals 1. What would Z have to be equal to in order for this equation to be satisfied? Quick, tell me, what would Z have to be equal to? So the point has to be on this, object, possibly a line. There you go, because 1 plus 1, so that's 2. So I'm going to need this to be equal to 4. So Z's going to have to be equal to 2. So there you go. 1 plus 1 plus 4 is equal to 6. Good. Let's pick Q, I don't know, let's pick X equals 2, Y equals 2. And so what would Z have to be equal to here?
1.
There you go. 1. So that works. And R, let's pick, I don't know, X equals 0, Y equals 0. So what would, what would Z have to be equal to? There you go. Have to be equal to 3. Okay, because 2 times 3 is 6. The other 2 are 0. So these are any 3 points. I just picked any 3 points. We could go on and on and on and get a whole bunch of points. But let's check what happens when we get PQ. Okay, so remember PQ, second minus first. So 2 minus 1 is 1. 2 minus 1 is 1 again. And then 1 minus 2 is negative 1. Now, let's try QR. Okay, so here 0 minus 2 is negative 2. Here is 0 minus 2 is negative 2. Oh my God, this is going to work. Oh my God. Folks. Are these two vectors parallel to each other? Are these vectors parallel to each other?
Yes,
Yes, they are, because multiply by 2. Well, guess what, folks? We just won the lottery today, okay? Because you probably had a sense here that this wasn't supposed to work. I guess I just accidentally happened to pick 3 points that we're going to pick. So just to show that sometimes things don't work out, let's pick PQR, let's pick point S, and let's find a third point. Okay? Sorry, let's find a fourth point. All right? So today might be the day to buy a lottery ticket, because the chance that I picked 3 points that would fall in a line, pretty crazy. Okay, let's pick, I don't know, X is equal to 2. Let's pick, I'm afraid now, I'm hoping this is going to work. Let's pick Y is equal to 1. Okay, so here, what do we have? So we have 2 plus 1 is 3. We need this to be equal to 3, so 3 over 2. Okay. Does that work here? 2 plus 1 is 3. 2 times 3 over 2 is 3. That's equal to 6. And let's find RS. And let's hope it is not parallel to one of these two. Okay. So let's do, what are we doing? RS. So second minus first. So 2 times 0 is 2. 1 minus 0 is 1. And 3 over 2 minus 3. So 1.5 minus 3 is negative 1.5. Negative 3 over 2. Is this vector parallel to the other two vectors? No, because you see here I'd have to multiply by negative 1 for the x's to work, and we see that the others don't work. Okay, so a little bit of a snafu. I guess I accidentally picked 3 points that were on the same line, but when we picked the fourth one, we saw that that is not along the same line. Okay, so this expression here does not represent a line in 3D. Okay, now does anybody recognize this type of equation where we might have seen it before? Does anybody recognize where we saw that type of equation in a previous question? Okay, well, I'll remind you. When we were trying to find, so don't forget about the pens here. I want you to just look at the tips here. Okay, one of the questions that we looked at earlier on asked you to determine all points that were equidistant to these 2 points. Okay.
Oh, was that the sphere one?
So not the sphere, because that was the points that were at a certain distance from one given point. Okay, but it was very similar to the sphere one. It said, here's 2 points. What are all the points that are equidistant to it? Okay, so for example, let's say these were my points, P and Q, and they wanted us to find all the points that were equidistant. So we realized, well, that point's equidistant, that point's equidistant, that point's equidistant. Okay. And we solved this problem. And when we solved this problem, we got an equation that had exactly this form here. Now, I remember somebody suggesting, oh, it looks like this is creating a line. Okay. But remember, we're in 3D. Are these the only points that are equidistant along this line? Well, what about a point somewhere up here that's the same distance to those 2 points? What about something further up that's the same distance to those 2 points? And then you start to realize that you're creating something that is much bigger than just a line. Okay? So again, I'm going to leave this as to what this equation might represent, because it is going to come out to be something very important for us. And it kind of makes sense that if this type of equation was important in 2D, that this equation should be important in 3D. Okay? However, what we've just established is that this does not represent a line in 3D. It represents some other object. Okay? So again, you might want to think about this problem again to see if you can figure out what it does represent. Okay? So I would definitely spend some time thinking about that. All right? So what this is telling us is that this approach doesn't work. Okay, it's I'm telling you, I'm implying that this is going to be an important equation. However, it's not important in that it defines a line. Okay.
Tony.
Yeah.
When we were talking about like the lines being parallel up there, how does them being parallel, if they were all parallel, would that indicate that it is a line?
Yeah, that if any 2 points that I pick would create a vector and all those vectors were parallel, it means they all lie along the same line. Okay?
Okay.
So that's the whole idea, is that if every set of points that I pick, those vectors, regardless of what they are all parallel, it must mean that those points all lie on the same line. However, as soon as I find a point where the vector is not parallel to those other ones, then they can't all be lying on the same line. Okay?
Okay, thank you.
Okay, so like I said, well, this was just really bad luck on my part. In fact, what I should have done is just looked at the solutions I created that I posted. Instead, I winged it, and it turned out I happened to pick 3 points that were on the same line. But then when I picked the 4th one, it was not along the same line. Okay? So the alternative I'm going to look at here is I'm going to try to use our other form of the equation of a line as some inspiration here. Because the other way in which we consider the equation of the line is this slope-intercept form. Okay? But what does the slope represent? What exactly does the slope of a line represent? So who wants to remind me? What in essence is it? What kind of mathematical object is it? It's a rate of change. Okay? It's a rate. It tells you, how, you compare the change of y to the change in x. You take this ratio, okay? And it's constant throughout the whole line, regardless of what your choices of points are, okay? The problem in 3D is that if you try to think about how the z values are changing with respect to time, okay, you're not just dealing with one other variable. You're dealing by trying to compare the change in z with respect to changes of x and y, in which case you can't write it as a single ratio, okay? So this idea of slope in 3D is not going to work, because a rate or a ratio is a comparison between two variables, not between one variable and two other variables. So what physical characteristic does the slope tell you about? So this is how it's defined mathematically, but what does it tell you about the line physically? So what information does the slope give you about how a line looks on the Cartesian plane? There you go. It tells you about steepness, okay? Whether it's increasing, whether it's decreasing. So I'm going to use that idea of steepness and increasing, decreasing. What I'm going to do is I'm going to describe that as direction. It tells you something about the direction of the line. So is it moving up? Is it moving down? Is it moving up at a high angle? Is it moving up at a very low angle? You can think of the slope as giving you information about direction, okay? So, and let's stick with 2D now, but the idea here is to start with something we know and then hopefully show that it'll generalize nicely into 3D. So I've got this line, and I'm wondering if there might be an alternative to representing this idea of the direction of the line. What might we use now to represent the direction of this line? What type of object do I now have at my disposal that describes in what direction this line is pointing? Okay, what about using a vector that's parallel to the line and have this represent the direction of the line? Okay, and this is the idea here. Okay, so remember that when we had the slope, there was another piece of information you needed. Was the slope enough to determine the equation of the line? No, you needed something else. You needed at least one other point. Now, I would say that the same thing must be happening here, because this is not the only line that's parallel to this vector. This line is parallel to the vector. This line is parallel to the vector, and so on and so forth. So if I want this specific line, I'm still going to need some point on the line, some known point. All right? And this is the way we're going to define this line. Okay? If I want to use this vector, well, I want to start at this point, and essentially what I would like to do is, to that point, I'd like to add multiples of this direction vector. Because remember, this direction vector can be moved onto the line, and I can add multiples of this direction vector. And look, if I add one of those vectors, I get to some point on the line. If I add 1.5, I get to another point on the line. If I add 2 times the vector, I get to a new point on the line. That if I add different multiples of that direction vector, I can get to any point on the line. And in fact, I can also get to points on the other side by multiplying some negative scalar to my direction vector. The problem is we don't add points and vectors. We add vectors with vectors. So the way we're going to describe this is we're not going to talk about the point on the line. We're going to talk about the vector to that point. Okay? So this is what we're going to call our R naught, the vector to a given point on the line. And what we're going to do to that is add some multiple of my direction vector. And since the direction vector kind of plays the role of slope, well, we use m, except with an arrow, of course, to represent this direction vector. So what I do is I take a vector to my known point and I add some scalar multiple of the direction vector, and that's going to take me to a new point on my line. And I can describe any point on the line using this vector addition. So this is just going to be r without the little subscript there. So remember, we often use a subscript not to represent a specific value, and this is going to be some random point on the line. So how do I get more and more points on the line? I just add different multiples of my direction vector. And this is what we call the vector equation of the line. Okay? So r represents the vector to any point on the line, and that can be written as r naught, the vector to a specific point, plus some multiple of my direction vector. And t can take on any real value. And as I choose different values of t, I get to different points on the line. Okay? Now, sometimes this is written more explicitly, where I say, well, if this is the vector to some random point on the line, say xy, this is going to be some given point on the line, x naught, y naught, plus t times, well, we have to give some name to this direction vector, and usually we call it vector AB. And this is how I can produce any point on this line. All right? Now, what I'm hoping you're going to see in this development is that we can do the exact same thing even when we go to 3D. Okay? Nothing that we did here specifically relied on any of these components being two-dimensional. Okay? And that's why this new view of a line, because part of you might say, well, wait a minute, we already have two nice ways of representing equations of a line. Why use a third? Well, because these first two did not allow for a generalization in 3D. This one will. Okay? So if we look at this example here, okay, it says let negative 3, 5 be a point on this line, and 1, 4 is parallel to my line. Okay? So guess what? That's going to act as our direction vector. How can I write an equation for all points on the line? Well, it's just going to be r equals, so remember this represents a vector to some general point on the line, is just going to be negative 3, 5 plus t times 1, 4. Okay? So this offers an alternative to the slope-intercept or standard forms of the line. Now, by the way, what line does this represent? What is the relationship between these two lines? Can anybody tell me what is going to be the relationship? Exactly, they're the exact same line, okay? Because in the end, you can use any point on the line and any vector that is parallel to the line. These two represent the exact same line, okay? Now, it means that if I want to get to some point xy, I'm not going to be using the same value of t in this version of the line as that version of the line. The t values will be different, but eventually this line and this line will produce the exact same points. Okay? And so now what we're going to do is just show that everything we just did, okay? So let's take a look. Doesn't this equation mean that the line always goes through the origin? Oh, not necessarily, okay? In fact, if we wanted to test if 0, 0 was on this line. Now again, I'm going to hope I didn't come up with something that happens to have 0, 0. Let's take a look. Okay, let's take negative 3, 5 plus t times 1, 4. Okay, so I want to see whether this is a point on the line. What would I do? Well, here, let's do the x values. So here, negative 3 plus t. And then this would be 5 plus 4t. Okay, and I want to see if this can be equal to 0, 0. So let's equate the x values. 0 equals negative 3 plus t. So t is going to have to be equal to 3. Let's do it now with the y's. 0 has to be equal to 5 plus 4t. But what happens when I try to solve for that? I get negative 5 over 4. Look what happens. Did I get the same t value that produces 0, 0? No. So what does that tell me? 0, 0 is not on this line, okay? Because it should be the same value of t that produces the x and y components, okay? So does that make sense that 0, 0 in fact is not on this line? Okay, so this is how you would show whether a point is on the line, is you'd figure out what t value is needed to get x and y, and it better be the same t value. In this case here, it's not. Okay? Okay, good question. So the reason why, like I said, this is useful is because you're going to see that I'm going to follow the exact same idea in 3D, and nothing is going to change other than having the extra component. Okay? Because now, if I've got some general line in 3D, I'm still going to use a direction vector parallel to I'm still going to use a direction vector that's parallel to the line. I'm still going to need a specific point on the line. And I'm going to use that vector, r0. And what am I going to do to this vector, r0? I'm going to add some scalar multiple of that direction vector to produce any other point on my graph, okay, on my line. Okay, so it's always vector to the given point plus or minus some scalar multiple of that direction vector. So here we have r, which will represent as some general point on the line. Okay. Okay, you need r0, okay, x0, y0, z0 is the vector to a known point on the line. Okay, I need my direction vector, which is parallel to the line. Okay, and then if I want to generate any point on this line, I have to use any real value of t. And the way we write the equation, so like I said, the vector equation is going to be r equals r0 plus t times m. Okay, or I can write it more explicitly. I can write it as x, y, z is equal to x0, y0, z0 plus t times a, b, c. And again. So this is what we call the vector equation of the line. But sometimes what we do is we write it as we had to do in this previous example, where to solve a problem, I had to work with the individual components, is sometimes what we do is we write it out so that the individual components are given. And this is what we call the parametric equation. Okay, where I say, well, what would the x value be? The x value would be, well, x naught plus t times a. Then the y value would be equal to, well, y naught plus t times b. And then finally, the z value would be z naught plus t times c. Okay, and again, t can be any real number. Okay, so this is sort of the simplest way of expressing the equation of a line in 3D. This is often the more useful one because you're very often working with the individual components. All right. So I know I'm going a little fast here. I'm just looking at the time. So let's maybe take a look at this question here. So they give me 2 points on the line. Let's see if that's enough information to find the equation. So clearly, I know a point on the line. In fact, I have a choice of 2 of them. So that's great. How would I find a vector parallel to this line, though? Who can tell me how I would find a vector parallel to this line? If these 2 points are known to be on the line. Anybody? Well, what about the vector AB? That's parallel to the line. What about the vector BA? That's also parallel to the line. In fact, any multiple of either of those vectors would work. So, you know, I could take one that's AB. That'll be parallel to the line. So let's see what we get. A to B, so we go backwards. -1 minus 2 is -3. You know, -5 minus -3, -5 plus 3 is 2. You know, 0 minus 6, -5 plus 3 is -2. And then here's 0 minus 6, -6. I could also take BA. That's also parallel to the line. Well, that's just going to be the opposite, 3, 2, 6. Maybe that's actually a nicer one to use. You know, I could use, you know, 2 times BA. 6, 4, 12. That would also work. Okay. So here it's asking me to find 2 vector equations. Well, I like this direction vector best. So maybe one equation could be, okay, R naught, let me pick this point, 2, -3, 6 plus t times 3, 2, 6. Or a second equation could be, well, let me just start with that point, -1, -5, 0 plus t times 3, 2, 6. Okay, I could have replaced the direction vector with one of those other ones. So what you're seeing here is that when it comes to equations of lines in 3D, you can have answers that look different, yet represent the same line. Okay, so I'm going to pick this first one here, and let's write it in parametric form. So the x value of my general point would be equal to 2 plus 3t. My y value would be equal to -3 plus 2t. And then my z value would be equal to 6 plus 6t. And this would be the parametric form. Okay. And the last thing I'm going to do real quickly, I know I'm conscious of the time, is there's actually a third form. It's not one that's used very often, but I do really feel I need to bring it up with you because the textbook seems to really like symmetric form a lot. And what symmetric form does is it says, well, let's take all of these x x equals 2 plus 3t. And what we're going to do is we're going to solve for t. So what would t be equal to? Well, it'd be x minus 2 divided by 3. And do the same thing with each of the expressions. Solve for t. Well, that's going to be y plus 3 divided by 2. And then here, do the same thing with z, 6 plus 6t. T is equal to z minus 6 divided by 6. But what is special about all these t values? They're all the same values. So another way to write this equation is x minus 2 over 3 is equal to y plus 3 over 2 is equal to z minus 6 over 6. And this is what we call the symmetric form. Okay? So here you see the point explicitly given. Here you see the point as the constant in each of the equations of the parametric form. And here you see the point in the numerator of symmetric form. For the, what do you call this? The direction vector, here it's explicitly given. Here it's the coefficients of t. And here it's the denominators of the symmetric form. Okay? So sorry for going over time there. So again, there's not going to be a lot of stuff on torque. You just need to be aware that it's the cross product of this r vector and the force vector. And depending on how the information is given, you would use either the algebraic or geometric definition. But the big thing for today is this new way of defining lines that allows us to come up with an equation in 3D. Okay? So definitely this is something you should be going over, and I think most of the questions from the homework correspond to questions regarding the equations of lines. Okay, any questions before we go?